Well, good morning, folks. My name is Ed Clark. I'm the director of the National Water Study, deputy director of NOAA's Office of Water Prediction. We're going to go ahead and get started this morning, and I will send Dan. He's been called away to an immediate meeting. So without further ado, I will thank everybody for joining us, particularly our deep core partners from the National Center for Atmospheric Research, our colleagues at NCAR, our friends from the U.S. Geological Survey, and our friends from the Army Corps of Engineers Engineering Research and Development Center. This is an exciting opportunity for us to talk about how we, the collective we, can engage in an activity that I think really lends itself to the development of a next generation federated set of water resources simulation, potentially. So before I turn it over to Trey, I just want to lay out a few of our principles here. That is that this is present at creation. We're asking and hoping that the community comes together to work with us to develop these sets of capabilities that transcends the mission of NOAA and the National Weather Service and can be applied to a myriad of activities related to the water resources realm across multiple federal entities and potentially even growing outside of that community to the academic and research realms. I do want to applaud the folks that have developed and engaged in the first proof of concept demonstration of efforts thus far. This is simply to us a advancement of a concept versus the beginning of a project. That project will really begin, that activity will begin as we engage with the community. So without preempting what Trey and Fred will discuss, I do want to just kind of welcome everybody to the first instantiation of the conversation and remind everyone that it is just that. It is the beginning of a conversation that we are hoping to work as a community, not just as an agency or an entity with an end goal, but as a community to evolve these capabilities over time. So with that said, Trey, I'll turn it over to you to get us started.
Thank you very much, Ed. And I would like to ask everybody to please be sure that you are muted. I really appreciate everybody's. We do have a lot of participants, well over 100. So I want to make sure that we're able to communicate clearly and effectively and not be subject to the background noise. So I would like to introduce the speakers for today's webinar, and this is all about the next generation modeling system that we are developing. Again, please mute yourselves. This seminar is about the next generation modeling system that we are developing. So I'd like to introduce today's speakers. My name is Trey Flowers. I am the director of the Analysis and Prediction Division at the National Water Center in Tuscaloosa, Alabama. We also have Dr. Fred Ogden, who is our chief scientist, Dr. Dave Blodgett, who is our USGS colleague and is one of the foremost experts in data models. We also have Nels Frazier, who is our chief software architect here at the National Water Center. So I will go ahead and get started with the National Water Model. Now, this is a modeling project that was directed by Congress in 2015. Congress directed the NOAA and its partners to begin development of this next generation system, or excuse me, of a modeling system that represented the continental scale water resources. So, sorry, okay. So directed us to develop a continental scale water resources prediction tool. And the result of that was the National Water Model. The National Water Model is a system based around the NHD Plus network that is represents almost 5 million river miles of water prediction. So it takes the forcings engine or forcings information from the operational weather forecasting models. It ingests USGS stream flow, and it uses the NHD plus hydrography data set as a unifying principle. The calculation engine of the National Water Model is here in the black box, and it's essentially made up of a series um, of, of dynamically linked processes. So we use NOAA MP as our column hydrology model. We have our overland flow as 1D diffusive wave model. We use a 2D Busenesque screen or routing scheme for lateral subsurface flow. We have a conceptual nonlinear reservoir for our base flow, and we have Muskingum-Kunj as our channel routing, and reservoirs are represented with a fill and spill methodology. So we have introduced the first version of the National Water Model in 2016. It is coming up on its 4th birthday next month. And we've been on a very aggressive release strategy. We have released 3 operational updates, and we are we're in science evaluation on operational update 4 that we anticipate for early in calendar year 2021. And we are in the throes of development of water model version 3.0 that we're anticipating in calendar year 2022 or perhaps 2023. That's still a little undetermined at this point. So we also have a community advisory committee for water prediction. And this is this is an advisory committee chaired by Don Klein of the USGS and by David Maidment, Professor Emeritus at the University of Texas at Austin. And they're a committee that comes together and provides non-consensus recommendations to the Office of Water Prediction for advancement of the National Water Model. So in 2019, after their last in-person meeting, they made several recommendations, and chief among these recommendations was the idea to go to a community development approach. And this is the idea behind this is to accelerate the development of the National Water Model. And they thought that we could do this if we articulate the requirements clearly, that we improve observational data, improve data assimilation, and we really embrace this community development and engagement process. And we at the Office of Water Prediction have taken these recommendations to heart, and we have started taking some actions that will bring these recommendations from into a reality. So one of those steps that we've taken is we have engaged along with our colleagues at USGS and at the National Center for Atmospheric Research, NCAR. We engaged the GSA's 18F group. They are a group of software designers, software developers, project managers, procurement specialists, and they've been charged with helping the U.S. federal government to modernize its IT infrastructure and software. And so they had several recommendations. They wrapped up their independent look at the National Water Model in late 2019, and they had several recommendations for how we could rapidly improve. And the ones that I want to highlight are number 3, which is to borrow from an industry open source development best practices. Number 6, which is celebrate the NWM community, and really to have a leadership and team structure that can help move us in a unified vision and direction. And along these lines, we had a design workshop about a year ago at this time, where we we got together the scientists from NOAA, scientists from the USGS, including some of their senior groundwater model developers, scientists from and software developers from NCAR, got together and came up with this initial concept of what a framework could be, and so, or what this next generation modeling system could be. And here's where our thinking was at that time: that it was a framework that allowed um, essentially infinite flexibility for the modeler to be able to represent a modeling problem in the way that they saw fit, and also which would allow almost infinite inclusiveness in the community. And so that's what it is. And what it does is it allows for substitution of any appropriate model. It allows for implementation of recognized concepts vetted through a community standards process. And guys, please mute. Ross and Zingtao, please mute yourself. Thank you. Um, So it allows for considerations of different methods for calculating responses of watersheds, and uses established methods to matter order and execution. So where we were with this particular design concept in July, we have been working very hard since then to evolve from that conceptual design to bringing this into reality. And I will hand over to Fred now to start talking about how we have built from this initial conceptual design, the feedback of the CAC-WP, the independent review from 18F, how we have amalgamated all of that feedback into this concept that we're now beginning to execute on. So Fred, please take it away.
Thanks, Trey. Can you all hear me okay?
We can hear you.
All right. So I have a few slides to kind of talk about the high-level goal that we're trying to meet by embarking on this activity. And I'm really pleased that we've got so many people from cooperating or agencies that are interested in working with us on this. This slide kind of talks about the motivation. I think that we can all use to justify uh, uh, participation. The first bullet, the federal agencies struggle with model selection, identifiability, and interoperability. I think that's a well-known quantity. It's a challenge that a lot of agencies face that really has at times seemed almost insurmountable. There's legacy codes that run in heterogeneous computing environments that impede advances. And a lot of those are codes that have evolved over time. They've got a lot of very specialized functionality that works well within that code base, but it's really difficult to make that work with another code. Uh, However, the contemporary open source software development paradigm encourages collaboration, evidence-based selection, identifiability, and promotes interoperability. And the best example of that is the Linux operating system that all of our supercomputers run. You know, it started with a student project back in the late 80s, and it has evolved due to the input of the community into the most probably, the operating system with the most hours of development in existence. It runs on Android phones and all over the place. Um, there's some really, another strong motivator is that there's a lot of overlap between our missions, and a lot of it is actually codified in statute that say, for instance, the Army Corps is required by law to use NOAA's streamflow predictions for operation of some of their projects. So we have a a vested common interest in trying to make our models as good as they can be. Next slide, please. This common need that we have really centers around the drainage network of the United States, and that is represented by the NHD Plus version 2.0, or the high-res version that Dave Blodgett will talk about. It really kind of forms a natural organizing principle for agencies that want to work together. Even though we have different missions and modeling needs and space-time scales of interest, if we can develop a computational framework or system that allows different process modules that represent or fulfill the needs of individual mission areas within agencies to interact with this network, it opens the door to a whole bunch of model interoperability. It also, if this framework is flexible enough to allow us to compare, say, different modeling approaches from different models or from the literature, it'll allow us to identify superior technologies. Next slide. So the proposed solution that comes out of the recommendations of the meeting we had with our partners last summer, the Community Advisory Committee for Water Prediction, and the 18F analysis, they all point to the need to develop a computational framework that allows arbitrary methods and models that simulate fluxes of interest. And it doesn't have to be water, it could be constituents, contaminants, sediment, etc. Simulate those fluxes and integrate them over arbitrary time scales and control volumes. So it really is kind of intersection of domain science, computer science, and data science. We kind of envision an architecture environment that appeals to domain scientists. So at the levels that domain scientists interact with the code, it should be very familiar. It should use contemporary open source software development methods so that anyone can check out the code, anyone can modify it, anyone can submit changes, and those are then available to the rest of the community for use in testing. The other thing is there's usually a testing process that goes along with a new submission, say called a unit test, that demonstrates that the code actually does something useful and doesn't break anything else in the code. And that'll provide maximum flexibility, it'll ease model interoperability, and it will allow evidence-based evaluation of different approaches and take advantage of each agency's considerable experience. And I think that's really powerful because every agency has codes that are demonstrated to do one thing really, really well, or multiple things. Next slide, please. The justification, at least from the hydrology standpoint, is that different hydrologic landscapes have different dominant processes. And the fact that there is this heterogeneity in process dominance, it affects hydrologic predictability criteria. Not all domains are equally easy or predictable. And the flip side of that is no model works equally well everywhere at all times. So there might be places where a particular model is particularly well suited, and it brings the question, we should probably use that model there at that time. In most locations, the surface and subsurface parameters are highly uncertain, which creates a really large parameter estimation challenge. Since I started developing hydrologic models in the late 80s, dealing with paper soil survey, county soil survey maps, and trying to estimate soil texture classes and parameters, it really hasn't improved much other than data access. Those maps have been digitized. There are some people developing parameter sets for subsurface parameters, but it's still largely a real challenging problem to get the values of that work well, particularly given that we've got uncertainty in the flow processes in the subsurface as well. The literature pretty clearly shows that models with fewer parameters generally outperform models with more parameters in all but catchments that have enough data to justify using more parameters. Research catchments, sure, there's really sophisticated models that have been developed and tuned for those. But in general, the concept of parsimony and Occam's razor both suggest that simpler is usually better. And then modeling success results from acknowledging the dominant influences of uncertainty and heterogeneity from the perspective of dominant process and predictability. So if you know what matters when, and you have a model that does really well at what matters at that particular point and at that time, you're more likely to have a favorable outcome in terms of a prediction. Next slide. So let's talk about the role of groundwater. That's a really important kind of bisector in hydrologic predictions. The aridity index has a dominant influence on the depth of water table in most places. It's not a universal truth, but it's pretty common. If it doesn't rain as much as potential ET in a given year, it tends to mean the groundwater table is going to be down from the surface farther than places where it rains more than potential ET. So this figure that I got from a paper by Zomer et al. 2008 clearly shows we've got this really wide range of aridity index, which means that there is a pretty significant variation across CONUS, at least, of the influence of groundwater on runoff generation. When the groundwater table is far from the surface, it usually means that the runoff response tends to be rain rate dependent, and that's a particularly challenging problem in itself. Next slide. Now this is a plot. The upper plot is using USGS data from gauges 2 reference gauges that have mean annual precip estimates. If you take the mean annual runoff and divide it by the mean annual precip, you get the annual runoff ratio. And you can see there's some pretty strong organization. If you keep in mind that aridity index map, there's a lot of coincidence. Look up the line of 100th longitude from Texas up into North Dakota. There's a lot of really low runoff ratio there, and that's right at the area where the aridity index becomes less than 1. The runoff ratios are really low there. The highest runoff ratios in the country are up in the northwest of the Pacific Northwest, where it just, it rains a lot, and it's usually in the cool season, so a lot of it is transferred into runoff. You also see some enhancement up around the Great Lakes, which is probably due to lake effect, snowmelt. And on the windward side of the Appalachians, there's some rainfall enhancement there due to orography. On the leeward side of the Appalachians, the runoff ratios really drop off, and that's the rain shadow effect of the Appalachians. You have intermediate values. The yellows are in the eastern half of the Midwest. There's a bullseye annual precip starting down about the head of passes where the Mississippi River dumps into the Gulf of Mexico, but it doesn't really show up on this figure because most of the rain, the predominance of the rainfall is in the warm season. There's a lot of ET in the southeast. And then in the Rockies, you see some really high runoff ratios associated with snowmelt dominant processes. Now, if you look at the lower figure, shows an analysis that we have done of the National Water Model version 2.0 retrospective run, which is 24-year simulation. And we went back and looked at warm season runoff events to see how well the model was doing in terms of predicting peak discharge. The larger, there's 2 different sizes of dots there. The larger dots are the ones that are within plus or minus 25% error. The smaller ones are ones that have a median error that's greater than plus or minus 25%. Red is an underestimation, blue is an overestimation. You can see the preponderance of the larger dots where the modeled prediction error is smaller corresponds pretty closely with the runoff ratio if you see it up above. So it just hints that the role of groundwater in the dominant runoff generation, which is a function of all those parameters that are listed there: soils, land use, cover, rainfall rate, freeze thaw, underlying geology, antecedent precip. It places an emphasis on different processes, parameters, and I would posit different model formulations. Next slide. Here's an example. This is from a paper that a former student of mine, Justin Niedzlik, published in 2004. He developed a 2D finite volume groundwater model to simulate saturation excess runoff. And we were thinking that the water table dynamics might be an interesting thing to think about. And what this figure shows, if you compare hydrologic predictions or stream flow predictions for saturation excess runoff, a finite volume model versus top model, the hydrologic predictions are actually really pretty close. I was surprised to see this result. The top model assumptions that the water table is always parallel to the land surface slope, that the transmissivity is uniform, the soil thickness is uniform, et cetera. Those assumptions are perfectly valid in certain situations. I was surprised to see that it performed so well compared to a finite difference model. However, if you look at the water table dynamics, as here we've got a plot of the fraction of the area of the water table that's saturated versus the soil moisture deficit. There's a huge hysteresis loop in the finite volume solution that's caused by, as the water table moves, as it rains, the water table rises uniformly, and as it falls, it preferentially falls up at the limits of the watershed faster, because that's where there's a no flow boundary condition, and it causes this big hysteresis loop. If you take the values, the internal state of top model, and plot it, you get those red symbols, and you can see that they're really quite different. So the top model doesn't simulate the water table dynamics correctly, but is that important? Are you interested in that aspect of it, or are you interested in stream flow prediction? So a certain model for like top model is computationally simple. Using it would save a lot of CPU cycles. If the groundwater table dynamics are important, you probably don't want to use it. If they're not, you could probably use it and have big improvements. And that's just one example. I'm not a top model evangelist by any means, but why wouldn't you want to use it in Sleepers River, Vermont, for instance? The other thing that I put in fractures in the bedrock here that would clearly indicate that, to a hydrogeologic standpoint, that the surface water and the groundwater basins might not be coincidence. So we need to be able to consider that in our framework as well. Next slide. So this leads to the notion of diverse model formulations, and this is a figure that I produced for a book chapter on hydrology. You have the real watershed with all of its surface complexity, and reservoirs and cities and agricultural area and forested areas and all of that stuff. There's a water table down there, some geology, a lot of heterogeneity in natural and anthropogenic factors. There's lots of ways that people have envisioned to deal with that. One is the hill slope. So there's Kinross or PRMS type approach, the tiled approach where you calculate the behavior of these different land covers differently. They don't really interact, but they're represented. That's another one. The structured approach, like Geisha or She, where you have voxels that you can simulate different areas and using different parameters. An unstructured or Voronoi type model, T-ribs, something like that, or 80 hydro. There are other models like Thales that use a stream tube representation. Some models actually use an isochronous representation, which is kind of orthogonal to the stream tubes. There's the good old conceptual model, and some places where maybe there's a lot of uncertainty, that kind of approach can have a role to play. Topographic wetness index models, there's several different models, top models, not the only one. And then machine learning, that's the new kid on the block, relatively speaking, where if you have enough data, you can train a machine learning technique to work. And we should be able to consider all of those, because there are probably situations where one of those is more appropriate or has lower uncertainty than others. And if we have a framework where we can test them, that will give us the ability to do that experiment. Next slide, please. My slide, okay. My slide is not changing. Trey? Okay, so the strategy, this is my last slide. The strategy that I've envisioned in coming up with my section of this talk was that I think we should try to form 2 design working groups and have a common coordinating group between them. One focused on the computer science and the other focused on the domain science. The data science kind of group would be kind of overlapping both of those. And then I think if an agency or a missionary is interested in participating in this, it would be helpful before we have any meetings if they would identify their specific needs. Here I'm giving an example of the needs that NOAA National Weather Service has identified. So this is an example set of the kind of high-level thinking that we've put into thinking about what we want to achieve with this software development. First is we want to allow evidence-based evaluation of 3 to 10 square kilometer catchment models over CONUS with hourly inputs that feed a refactored NHD plus computational hydrofabric. And Dave will talk about that a little bit after this. We want to develop process level libraries of hourly or finer flux calculators. So these are the standard things that everybody has to use in their models, or they could be non-standard. But to get out of the business of rewriting the Penman-Monteith equation over and over and over again, and have it as an open source piece of code that is library callable. It might even exist. We just need to find it and bring it in and make sure that it works with our system. Snowmelt's another example. There's a lot of different snowmelt models out there. It would be great to have those as library functions so they could be tested in a plug and play environment. And then we'd like to have process level libraries of integrators and solvers. For instance, we would probably want to implement explicit finite volume very quickly, but others would be useful as well. We would also like our framework to be able to support whole model realization. So if there's a particular model that we'd like to test and evaluate in its standalone code, we'd like to be able to perhaps wrap it and put it into our framework for testing without having to turn everything into a library that's in that code. If there are parts of it or all of it that we like, we could probably think about converting it into libraries. Then other models could call some of its functionalities. And we want our solution to be compatible with the National Water Model Forcing Engine and its outputs. So that's a really important part of our operational mission. So with this, I'll turn it over to Dave Blodgett, who's going to talk about his work done over the last 3 years, starting with a sabbatical he spent here at the National Water Center at trying to turn the NHD Plus into develop a set of tools to convert the NHD Plus into a computational hydro framework that's a little bit more amenable to computation. Dave?
Cool, thank you. So thanks to everybody for being here. This is a really impressive. I'm looking at 158 people on. I'm absolutely flattered to be able to present to you all today. So Dave Blodgett, if you don't know me, trained as a civil engineer, University of Wisconsin-Madison, environmental fluid mechanics, developed a horrible data habit over the years, and am now doing all sorts of silly things with hydroinformatics. Running off to an ESIP presentation on structured data on the web immediately following this webinar, just to give you a taste of where some of my interests lie. But So I have this. I want to start what I'm going to talk about with this one top question, and I actually just realized, Trey, if you can pop back 2 slides, this question actually has a lot to do with this graphic, and there's an implied assumption that all of these have, right? These are all representations of what we refer to in the OGC and soon to be hopefully World Meteorological Organization standard HY features. These are all representations of the hydrology phenomenon. Hydrology phenomena, you can call it plural or not, but and go ahead back to my title slide. I just want to kind of make that point that these are all ways of seeing the phenomena of generating stream flow. And I think we can go ahead and jump in. So the answer to this question is because hydrology, right? And before the groundwater folks start to throw tomatoes full of groundwater, so it's very important to recognize here that the abstraction that we're starting from with this work is stream flow. And yes, rain goes into the ground, goes into a groundwater system that may or may not be coincident with the surface water basin, and might come back up somewhere else and contribute to stream flow. And that's something we have to represent. And it's a complexity that we're going to have to handle in how we couple our surface water and groundwater representations of hydrology. But just come back to, we measure stream flow, and that's what we're really focused on here. So let's carry on. So I have 4 framing questions just to kind of get everybody to this is expanding on that first question is why is fluid at a gauge affected only by its watershed? Well, let's tease into that a little bit and think about it from a few perspectives. So if you're a hydrologic engineer, you're interested in control volumes and the boundary conditions on those control volumes. If you're a web developer, you're interested in resources. So uniform resource locators, URL, is a locator for ostensibly a digital resource. And how do those resources link to each other, right? How do we provide information to our stakeholders over the internet in a way that's consistent with our understanding of hydrology? From a software development point of view, what modules or objects are you going to include in your software, and how do those modules interact with each other? From a data science or a data engineering point of view, what's the schema you're going to use? What's the ontology you're going to use? And how do its entities relate to each other, right? So these are 4 questions that use different language, but they're essentially the same question. There's some diversity in how you would answer them with regard to the use cases where you're going to apply them, but the notion that we're using here and the notion used in high features is that the same concepts apply. So next slide. So I'm going to step back a little bit and just kind of remind everybody that there's a long-term big picture here that we are building on. We are by no means doing something new. I remember sitting at a dinner with David Maidment when he said, let me tell you some history about hydrography. And he relayed to me how the first national hydrographic data set was a thing that you had to stand over somebody's shoulder driving a mainframe and look at on a 2-color display. And that was only like 30 years ago, right? So 20 years ago, it was novel that we had a national observations kind of backbone from NWIS. It was novel that we had a national NHD Plus in the works. So 10 years ago, NHD Plus version 2 was getting its legs underneath it. We were hardening up our data services for streamflow observations. And we started to work on and set the stage for a national model from a computational point of view. So 5 years ago, that model started running in operations, for what it was, and it was a huge accomplishment to have a national NHD Plus version 2 scale streamflow model up and running. it's been updated more or less annually since then. And now, we're in a position where we can generate a hydrologic geospatial fabric at basically any resolution based on NHD plus version 2 with a path to high res. And that has all been done in the context of this ongoing, not always easy, but this ongoing planning process between the Office of Water Prediction, NCAR, and USGS and partners that have come to the table as much as we've been able to find opportunities to do that. So next slide, please. So now let's dig into a little bit of context. What's actually been done here? So this was what I was really focused on primarily when I was on detail with OWP at the Water Center. I was 50% USGS, 50% Weather Service. And basically the observation we had was, look, NHD plus, this has got a bunch of truncated ones on the upper left histogram, but the distribution of flow line length is very broad in NHD plus, which isn't ideal for a number of reasons from a modeling perspective. So can we tighten up that distribution? Can we get rid of some of these teeny tiny catchments that are unnecessary? And can we split up some of these greater than 10 or greater than 2 or 3 kilometer long catchments? And the answer is yes. It's not rocket science. It was some coding. It was interesting. And we can tighten that distribution up. And that's going to open up a lot of potential in terms of hydrodynamic routing and making sure that our catchments aren't too large for runoff generation. So next slide. So getting into the details of how that works a little bit, we've got software now, and this is all in the open source, written in R, spatial. We've got software now where we can split catchments up using flow direction and flow accumulation. Next slide. We've got the ability to do this at a system level, so we can split catchments up. We can collapse them together, so eliminating little tiny catchments that are just kind of an artifact of a confluence and aren't necessarily hydrologically significant. And we can aggregate and or split. So this is for the kind of left bank, right bank view of a catchment. We can or lumped distributed parameter kind of modeling. So this tool chain, there are, so HY refactor is the kind of central package that's being used for all this work. And this toolchain works at continental scale with NHD plus version 2 and is being applied to other data sets as we go forward. So next slide. All right, so zooming forward here to NGen release 1. So this was kind of a proof of concept release on this NGen concept that was planned between USGS, NCAR, and OWP. And my contribution to this was to take the outputs of this HY refactor workflow that I just kind of walked through a few examples of and get it into a graph-oriented and open geospatial standard kind of model input format. And this is very much a work in progress, but it got us to a place where we had a graph of catchments, a graph of flow paths, the intervening connection features, so what in HY features are called nexuses, and connected stream gauges. And so this is good. This is available for you all to poke at. It's another R package in my personal GitHub called HYGeo. And so this was cool, done, great. Solved some interesting problems, discovered a few more interesting problems to work on going forward. Next slide, please. So far in NGen release 2, we've really started to zoom in and look at this issue of kind of scale of different representations of hydrography. So in this, what I'm showing here is we've got a mapping between NHD plus version 2 and NHD plus high res. And then we mapped the outlet locations along NHD plus high res flow lines onto NHD plus version 2 flow lines as events. So now we know precisely in a linear sense how these two networks relate. So say we have a hydrodynamic or flood inundation representation or model on high res, we can get the flows from medium res over into the other network. All right, next slide. So now we're going to step back again and kind of come back to the hydrology phenomenon. And I want to talk about HY features just a little bit, because this is really formative for what we're talking about, and it's the thing that allows us to share concepts across these 4 disciplines, or these 4 domains of kind of web data, hydrologic engineering, data science, data modeling, and software development, or modeling software development. And it's rooted in observational hydrology, right? We measure flow that is the result of the hydrology phenomenon at a watershed outlet. We measure or predict flow. That's very important. Measure or predict. And so those are the result of upstream processes. Okay, next slide. So how do we abstract those upstream processes? How do we talk about those upstream processes from a conceptual point of view across all 4 of those disciplines, right? Well, there's this top level concept in high features of catchment. It's completely holistic in the sense that the catchment concept is composed of a number of different functions that a catchment can complete or can do, right? The 2 that are most important, the two what we call realizations of the catchment concept that are in the kind of next gen framework are the notion of catchment area, which is the land surface and land surface processes, and flow path, which is the kind of a linearization of hydrologic connectivity, right? And so flow path is really just saying we get water from the inlet of a catchment to the outlet of a catchment. There's much more to how water moves. So there's an additional feature type called water body, which could be a lake, could be a river. There's a number of types. There's subclasses of water body that represent different kinds of kind of hydrodynamic or hydrostatic features. And then there's a separate feature from catchment, and the indentation here is actually purposeful because catchment and nexus are at the same kind of level of abstraction, or the same meta level. So nexus is a feature that connects one catchment to the next. So that's a place where, and so from a model software point of view, a nexus is a feature or a modeling class that helps you connect 2 catchments together, or connect a catchment to a downstream water body, say at the coast. And it's very important. So from an engineering point of view, this notion of a nexus is kind of a tool to allow us to build these multi-model systems that represent different conditions, whether it's different hydrologic landscape conditions, different types of hydrodynamics, whatever our transitions are, the transition happens at a nexus. Okay, next slide. And there are some, I believe we're going to distribute these slides, and there's some hidden slides with a few more details that we just jumped over, just so in case people want some more detail. Okay, so I just want to talk about this kind of holistic feature type a little bit as a bit of a segue. And I'm using, so this STAR class is roughly equivalent to concept. The language here, because the high feature standard is meant to be applicable across all domains essentially that deal with the hydrology phenomenon, it's a little awkward to talk about this stuff. So you can replace the word class roughly with concept or various other terms. But we'll talk in kind of object-oriented software terms. So a catchment class is realized by classes that do catchment stuff, right? So we might have a thing that does catchment stuff, and we refer to it as a realization of a catchment, or a realization of the catchment class, catchment concept. Similarly, a nexus class is realized by classes that do nexus stuff. So we might have a particular class of nexus that knows how to take a 1D hydrologic routing scheme.
These pictures on here all the time. I don't know.
Oh, we've got somebody way off mute. I think Noah. right. So this is something of a segue into what Nels is going to talk about later, because this really speaks to the modularity design. And the last thing I'll kind of reiterate here is, this catchment, this notion of catchment and the notion of catchment area. A catchment area has interfaces to groundwater, and a catchment area has interfaces to the atmosphere. Similarly, a water body, which is a high features class for doing routing, would have interfaces to groundwater and may have interfaces to atmosphere as well. And so this is not to exclude any of those other domains of modeling. It provides interfaces to plug things together in a way that's consistent. So next slide. All right, so each of these sections kind of ends with a little bit of a kind of here's our strategies for progress from the perspective of the material we're presenting. So I have a few here. So the top one is just to recognize that we are decomposing this problem for a number of reasons and in a number of ways. So clearly we're decomposing it spatially. And I would say it's for both social and engineering reasons, right? If we spatially decompose the problem, we know that we have basins that are autonomous. They don't interact with each other. So for engineering reasons, we have the ability to parallelize things. We have the ability to do all kinds of things because we can make multiple unique problems out of one big problem. But then there's a social side to that as well, right? We can send a subdomain of the model off to a hydrologist that knows a particular place very well and say, hey, can you help us make this better? And then we can take that back and put it back into the system. And we can use that spatial disaggregation or decomposition to our advantage. The second way that we're decomposing this problem is through kind of hydrology concepts and module decomposition, which allows us to then recompose the system out of various parts that happen to work together, right? And so recognizing that we're decomposing the problem in these two ways is really important. And I think we just need to embrace that, right? And lean into this idea for design purposes. And there's a lot of value to be gained there. Next slide. So this notion of a common data model is really important. And I think we all kind of get this. There are a number of kind of mathematical reasons for this, just in terms of the number of adapters you need to get everything to work together. But we just need to look for these efficiencies as we go forward. And when we see them, I think we just need to jump on them. So we can get next slide. And this is where I and pass off to Nels. But this echoes what Fred had said in different words. So within any one organization, we need to own the problem we solve for our stakeholders, in terms of that's the thing that we need to hold up as the value we're providing to the world, right? But we can't all re-implement the technical solution for the country. So we need to find ways to share the technical solution, and to some extent probably minimize the amount that we talk about the technical solution, so that we can own and talk about and be proud of the problem that we solve for our stakeholders using a shared tool. And so that's not easy. It's going to take a lot of humility. It's going to take some investment in teams and time, and having good both internal ability to kind of share vision and an ability to represent that vision to the community. But it's really crux. It's really important that we can kind of focus on the value that we're providing to our stakeholders while building a shared technical solution that can provide value for everybody. So with that, I will pass it off to Nels.
Thanks, Dave. I found my unmute button. So I want to talk a little more detail on sort of this framework idea putting into practice, into actual code and software, this conceptual idea of holistic catchments and these abstractions from that software engineering perspective. And I provide you guys with a quote here from a very popular design pattern book on software engineering, that the applications are hard to design, toolkits and libraries are harder, and frameworks are the hardest of all. So, we're talking about one of the hardest things to design in software, coupling that with the very wicked problem of hydrology. And so my proposal is to forget the hydrology and let's just build pizza. The joke aside, this idea of a framework, thinking about it in terms of a very simple abstraction of how do we build pizza, translates very well to how do we build a holistic catchment. We know we have some very simple abstractions for the steps we need to take. We need to be able to put together the crust and the land surface. We need to be able to say, I want this special type of sauce or this special type of forcing on my catchment. And then we sprinkle some toppings on. And really this comes back to the process representation and how we compose together different processes in a catchment. That's everything you see on the right here. That's how you make your specialized pizza that we can then put back into this framework, put into our oven, bake it, and send that down the line. Go ahead to the next slide, please. What we really want to focus on in this framework is the software engineering best practices. So this diagram here is a very high level view of a representation of high features that we can use in our software. We have each of these little process modules that are self-contained, that are isolated, that have a well-defined interface. We can compose those together to form a realization. And again, this is like, I've got my catchment area, I've got my land surface, I want to sprinkle that with these toppings. And then we're going to communicate those, through these good design principles, through design patterns, so that we can reuse parts of our code and parts of our framework to rapidly develop new pieces. The one thing I wanted to really point out here is that each of these components by itself requires a cohesive interface and design, so that when we go to put all of these parts together, they fit well, they're isolated, the details of each component are conceptually solid behind the piece of code that's supporting that. So I'm going to show that a little bit in this next slide. When building architecture, building framework, these pink lines in this animation are what that framework is. That they are responsible for that model control, that execution, for moving data, for moving inputs. That's our pizza oven. A very simple example here. The catchment and nexus realizations are what our community is bringing together, what our domain scientists are cooking up, that are following these patterns, that are implementing our abstract interfaces in a way that allow us to make each of these catchments a unique realization, a unique model, that are coming together, moving information through our system to our nexuses, that creates an independence of the implementation details. And this provides us localization of changes, rapid development and iteration on a particular realization. And that's our decentralized development. Go ahead to the next slide. So this comes back to the same issue that both Fred and Dave have talked about, is how we decompose the problem. And I want to go all the way back to our introductory remarks from Trey on our 18F process, and remember that we need to treat our interfaces as products. And so, all of this design, this implementation, these patterns that we're trying to focus on and get right from the beginning, follow these high features concepts and allow us to build the holistic catchment abstraction which can emulate and encapsulate the physical world that we're trying to model. And these conceptual boundaries that are in place in our data model inform the functionality and the data that various components need, and allow us to really focus on those dependencies as interfaces. Once those interfaces are designed and well thought out and put in place, we gain the encapsulation and composition and this sort of information partitioning that's very useful in the operational system and ensuring the quality of our software and our models and their outputs, but also unlocks this modularity and flexibility that we're hoping to gain. So go ahead to the next slide. And this is the bigger picture of what all of that looks like. And I don't want to spend a lot of time or detail on this, but really, you know, we are trying to decompose the problem from a domain science perspective into a software engineering perspective, all rooted around these same organizing principles, the realization, the composition of parts. Again, we're trying to define the recipe for our pizza, put it in our oven, and let the oven bake and serve that for us in a meaningful way that provides a separation of concern between what we're doing and how it ultimately gets served. Let's go ahead to the next slide. What we want to get started on now is really the community foundations. And so this figure on the right is the power law of participation. And I come back to this a lot in trying to figure out, you know, even how we communicate, how we get engaged, how we get involved, and really build out a collaborative intelligence. How do we come together around these shared problems and shared technical solutions and create our unique value? And that's through this collaborative intelligence. That's where we get that shared infrastructure, that shared technical solution. And I put an arrow on here to say we are here. We're somewhere between, you know, thinking about the problem, discussing the problem, prototyping the problem, sharing this work. And from the development perspective, really what we're trying to build alongside this framework is a software development kit. The only way to be successful in this work is to provide extensive documentation, examples, you know, tools and scripts to help ease the development of domain scientists into how to create realizations and get them into this pizza oven of an example. You know, what can we do in these sort of software engineering best practices to help accelerate this process? And some of that comes through static code analysis, best practices, auto formatting, you know, automated testing. The testing part is, I think, especially important as we start talking about large potential community contributions of how do we have confidence in those early and often. And we can do that through good practices in both unit testing and integration testing, and then also providing a rigorous but inviting review process. You know, how do we discuss amongst developers at different agencies on the best way to do something, or the best implementation or the best use of our framework, and that comes through a good open form of communication. So thanks for the slide advance there. It was well timed. I just put together a little graphic to kind of show what a software development kit entails, you know, graphically, and that is this large block of a framework on the back end that in front of that and in support of that framework are all of these concepts that are in place for the support of developers, contributors, scientists, you know, social scientists, data scientists, domain scientists, computer scientists. They all benefit from this. So I wanted to impress on the amount of work and collaboration that has to go into getting all of this right and getting started on these conversations early to make progress going forward. Go ahead to the next slide, please. So, in our last few minutes here, and I wanted to leave just a little bit of time for some discourse, I just wanted to show a little bit about where we are now. And we've gone through some initial design and prototyping work, trying to build out some of the core of this framework and tooling and documentation around that to help get started on how do we bring this framework to a point where we can work on it progressively. Go to the next slide. And so I took some screenshots of some of our open documentation here. So we do have automatic code documentation and generation. Every code change that goes into our repository triggers an automatic build. And then this is hosted just on a GitHub page. So we're trying to make sure that we're cognizant of bringing that documentation alongside of our code and our development strategies. Next slide, please. The automated testing, again, is another thing that I think is very valuable, and making that testing and the understanding of what that means publicly available. And so here it just shows on our landing page for our code repository, some automatic badging that just says, yes, our documentation builds are working, and our unit testing is passing all of our tests for the current state of the code. Go to the next slide. And this is just a sample of why that testing is important. And this shows for various contributions to the code what failed and what didn't. You see the red X's show that, hey, this contribution, this change to our code broke the tests. And so we have to go back and fix that before we integrate that change. We get it back to where we're passing our tests and we have more confidence in that framework and what is happening there. So sort of the strategy coming out of this initial work that we've been successful in some prototyping and some development with is really to get working groups in multiple domains to continue progressing the design and implementation of this complex yet well orchestrated framework. This comes down, at least on the raw development, what we can do to support the domain science is good use cases and user stories to tell us what features of our framework are useful and what aren't, what functionality is missing, what would help better facilitate development of new modeling and new techniques, and then really trying to come together as a community as leaders of hydrologic modeling and collaborate on road mapping these priorities and these features to a shared technical solution. Like I said, we have a prototype in place, but we know it's not complete. We know it needs work, and we know there's features missing, and there are parts of it that we haven't done well, and there are parts that we have done well. And we want to make sure everybody is able to get in on the ground floor of this construction and have their voices heard. And for technical contributions, I just wanted to put a link here for anybody that's interested in going to look at this later. We do have some contributing guidance on what you can do for very technical contributions, but I think we need to also further this discussion higher up and really come together and say, how do we make a commitment to work together to build this technical solution?
All right. Thank you very much, Nels. Really appreciate all of the speakers for adding their expertise and their own unique perspectives on how to achieve this or how to achieve this technical solution that everybody can participate in. I want to emphasize some of the last points that Nels brought up here is that we've had some initial success. We have a proof of life that we can indeed have multiple realizations of a hydrologic process and synthesize that output using using the data model and the framework that Dave and Nels spoke to. So we are still very early on. I think a group of roughly 8 or 10 folks have spent about 10 weeks on this project so far. So we are still very much in the ground floor, and we want to emphasize that we're very interested in building upon this initial success with the partners that are on the phone here. That's across the federal government, the USGS, the Army Corps of Engineers, our other colleagues within NOAA. That's with our partners at NCAR, and really with whoever wants to come and contribute to the success here. And the next steps that we're going to take is we're going to start doing some very targeted outreach with our partners. We're going to arrange scoping, next steps discussion with you in the future, and so be looking for that. With that, I would like to start opening the discussion. I know that Gaurav has asked a question in the chat here, and I also saw that Karen Bareford raised her hand. So, Fred, maybe you can take Gaurav's first question, which is really related to the concept of when you say anyone can make changes. I think he's asking more about that those changes can be managed within the community repository, but only certain things are going to make it into an operational model. So Fred, would you like to expand on our thoughts on that, please?
Yeah, sure. Every unique mission within different users of this, and it could even extend to private industry, may have, because the code's accessible, they might make modifications to the code that fits their need very well. We would hope that they would, if they do something that's really cool and interesting and they can demonstrate that it works well and that it does something better than something that the model already does or adds a new functionality, they could submit that for consideration into putting in at the very highest level, at the operations level. Of course, every agency will maintain ultimate control of what gets pulled into the code then. But I think it, going with having the door to the kitchen open so that anybody can come in and try their ideas is going to do nothing but help. So with that, what other questions do folks have? And with this many participants, I think we probably favor questions from people outside of NOAA or outside of OWP, because we have plenty of opportunities within OWP to talk about this. I'd like to use this venue to communicate with people outside of OWP. So I'll open the floor up for questions.
Thank you.
You could type them in the chat, or you could unmute yourself and ask it. Please, if you do that, say who you are.
Thank you, Fred. Karen did mention that her question was what was inadvertent. So the floor is indeed open. We do prefer chat questions. I can moderate that, or if anybody wants to unmute and ask, please feel free to do so.
And while we're waiting, I would like to add that we've gone out of our way in this presentation, as Trey said at the end, that we are just getting started, and it is a very good time to engage with folks from different agencies who are very interested and want to contribute to the philosophy and design of this from a very early level, to make sure that we'd like it to. It would be really nice if we could enable everything. Now, that's a pretty tall order, but if we could make it so that at least we don't prevent an agency from using the system to fulfill their mission, that would be a big advance. So getting voices at the table early on is really important. Any questions? Groundwater fitting in. Okay. So Aubrey Duggar asked a question from NCAR. How do we see about groundwater fitting in? I think, like we said, the groundwater basins and surface basins don't have to be coincidence. If there's a surface hydrology catchment overlying a region that, say, has a regional groundwater model, we should be able to couple to that. Those are pretty hard to find. the sky's the limit. If somebody wants to come up with another conceptualization of groundwater, it should plug into this framework.
Yeah, I would follow up on that a little bit and say, in development of high features, we had groundwater explicitly defined in early versions of the spec, and kind of got slapped down by the groundwater modeling contingent in the hydrology domain working group at OGC. And we kind of came to the conclusion that, well, there's clear connectivity between catchment area, functionally catchment area things and functionally groundwater basin things. And teasing out the details of that is something that it's going to take some work if we really want to get into all of the nuanced kind of, what is karst, what is a spring, what is a recharge area, those kinds of details. And I think that's going to be a really interesting area of work. That some of what we're doing now is that some of this is actually setting the stage for those more detailed conversations about model coupling to go forward.
Okay, there's no other questions in the chat.
All right, any questions from participants on the webinar that people want to ask by voice?
Hey, Trey, Fred, and company, this is Tim out in Boulder. So I was just kind of wondering a little bit about, obviously this is water focused, but I could envision a lot of agencies, your own included, in wanting to look at this as an Earth system approach and bringing in other processes and efforts, ecosystems, biogeochemistry, whatever. So have you guys had a chance to give much consideration to that? Well, UFS, of course, being another big one for NOAA. So have you guys interacted with those communities much or given any thought to that?
Tim, that's a good question. The Earth system modeling community is most oftentimes interested in longer time scales and larger integrated responses. We have stated as an objective of this framework that it should enable that kind of thing, but because of our mission and the fact that we're the water equivalent of weather prediction, and whereas Earth system modeling is more the climate analog for hydrologic prediction with a more research focus, it's entirely possible that our framework could be useful by those folks. But I think from the standpoint of at least the discussions we've had with USGS and Army Corps, that the shorter time scale is probably going to be more interesting to us immediately. So we haven't engaged with those folks yet, but that's definitely something that we could do.
Thanks, Fred.
You bet. Any other questions out there? So hearing none, I think Tom Graziano is on. I was wondering if, Tom, you'd like to add your comments to the discussion.
Sure. Thanks, Fred. And sorry, everybody, that I had to join late today. But with regard to Tim, your last question, I would say that to follow up on what Fred said, is that, we certainly want to see this effort be on a glide path that supports, easy integration, or as easy as possible integration into an Earth system prediction capability. In terms of NOAA, of course, that is the UFS, or Unified Forecasting System, where we're looking to first integrate on the atmospheric side of the house, and then couple that with terrestrial, ocean, and cryospheric type prediction. So certainly we have an eye on that as we move this effort forward. And I guess second, I would just like to say this was quite a turnout today, and really glad to see this many folks involved. And as has been mentioned a couple of times already, this was a first step, a sort of a proof of concept that we could employ an agile development process successfully toward this end. And it's something that we're really excited about building upon, and more and especially excited about doing that in collaboration with the other entities, who are participating today, NCAR and USGS and the Army Corps. So we think, I guess I'm reckoning back to Don Klein to a comment I guess you made on the third day of that you made, not I guess you made, but you made on the third day of the IHTM meeting last year, where we talked about you mentioned we don't have 10 years to do this. We have, we've got to do something much more rapidly. And so, we sort of see this as a pathfinder activity to sort of jumpstart and accelerate this effort in a collaborative fashion among the agencies. So anyway, again, thanks to everybody for your participation and support, and really look forward to a stronger collaboration moving forward. And I think you can expect to see from Fred an invitation, at least with a smaller group, to examine next steps and as we move this effort forward. Thanks.
Thanks, Tom. So I think unless anyone has anything, another question, I would suggest we adjourn, and you'll be, I look forward to interacting with some of the folks that are collaborating agencies to talk about next steps.
Well, thanks.
All right. Well, thanks, everyone.
Thanks, everybody. Have a great day. Appreciate it.
Thank you. And I do want to mention, this is Trey one final time, that we have recorded the webinar. We will be making the recording available, and we will be sharing the slides. For everybody who has participated, we'll let you know where the recording and the slides can be accessed. So thank you very much, and we look forward to working with you on this in the future.
Cool. Thanks, everybody. See ya.
Thank you.
Thanks.